Great, thank you very much. I wanted to thank the organizers for organizing this conference. So, and I wanted to start out by saying everything I'm going to be talking about is joint work with Milena Paviniak. Okay, so I wanted to start out with the basic objects that I'll be looking at, and I'm using terms a tiny bit non-standard. So by symplectic toric manifold, I will always mean a 2n dimensional closed connected manifold M. So people don't always insist on this, but I want to. And I want to have an integral symplectic form, omega. This relates back to Benjamin's talk, why I need this. We may be able to get rid of it in the future. A faithful S1 to the n action, and a moment map mu from M to Rn. It doesn't matter too much, but the convention I'm using is if you take omega and you input the vector field from the jth circle action, you get minus d of the jth coordinate of the moment map. And then we'll talk about the moment polytope, which I'll denote by delta, and this is just mu of m. And this is well known to be a convex polytope. And the two facts due to Delzant. And the first is that two symplectic toric manifolds are equivariantly symplectomorphic exactly if their moment polytopes differ by a translation. And a consequence of this is that all symplectic toric manifolds are projective varieties. So by this, I mean that we have it's an algebraic, you can give it a structure as an algebraic variety and you can embed it inside projective space so that its symplectic form is just the restriction of the Fabini-Studi form. And I will be doing that a fair amount. Okay, great, so, oops, sorry. There we go. Give some examples of symplectic toric manifolds. So the first example I want to think about are Hirzebruch surfaces. So consider the Hirzebruch surface sigma sub m. And what I want to do is I want to take the line bundle O of negative m over, which is the holomorphic line bundle over P1 with Chern class minus m. And I want to take the direct sum of that with C. And then I get a C2 bundle over P1. And then I'm going to projectivize that bundle, and I get a P1 bundle over P1. So my claim is that this is a symplectic toric manifold. Of course, you have to choose some embedding to get the symplectic form. And the action is pretty easy to see. So you have a circle action on the base P1, and these bundle, it lifts to an action on each of these line bundles, and therefore an action on their sum, and therefore an action on their projectivization. And that's one of the circle actions. And the other circle action is you just spin the fibers. So each fiber is at P1, and you just consider the natural action on that. So the moment polytope of all of these is always a trapezoid. So I include rectangles and squares as trapezoids, of course. And the coordinate ring has a very, very easy description. It's just two generators, each in degree 2, x1 and x2, and then x2 squared is 0, and x1 squared plus mx1, x2 is 0. And so the example you might want to think about, there's two important examples. Well, there's many, I'm just drawing two. One is P1 cross P1. So of course, in general, you get any rectangle, but here is an example of a rectangle you might get. And if we take sigma 2, we see it's similar, but you can see this line here has slope 2, so, or negative 2. Anyway, so the subscript is telling you how steep this line is. So those are Hirzebruch surfaces, and then we can generalize those to Bott manifolds. So we just keep on going, basically. So we define a Bott manifold, M, which is going to be the xnth inductively. So you start with x1 is just going to be a copy of P1. And once you've constructed xi minus 1, you take any holomorphic line bundle, L over it, and then you add a trivial line bundle. So now you have a C2 bundle over it. You projectivize that, and you get a P1 bundle over xi minus 1. So what you're going to have is a P1 bundle over P1 bundle over P1 bundle, blah, 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 blah. And properties is these are also symplectic toric manifolds, and the action is basically the same. You just do it in stages. And the moment polytope delta is always going to be combinatorially equivalent to the hypercube. So what this means is that you'll have 2 to the n facets, and they come in pairs and opposite pairs and don't intersect, but otherwise every combination of faces intersects. So the next 2 bullets are kind of explicit. If you've never seen this before, the point is just that this is explicit. So we can write delta as the set of P and Rn, which satisfies some formulas. So the inner product of P with Ej is bigger than or equal to 0, and the inner product of P with Ej plus the sum over I of Aij is less than or equal to lambda j for all j. And this is for some strictly upper triangular integral matrix A and lambda and Zn. So for each one, you're going to have this unique matrix and lambda. And the other thing is that the cohomology ring is very explicitly given. So you'll notice this looks like what we had for the Hirzebruch surface. If you've seen this, this is just Danilov's theorem. If you haven't seen it, that's fine. It's just the point is here, but it's a very explicit presentation of both the cohomology ring and the symplectic form in terms of these invariants. And one important thing is that this xj is a very specific element of cohomology. It is like a named known element of cohomology that I can point to. And it's the Poincare dual to the preimage of one of the facets in the jth pair. So these are the objects that I'm looking at. Are there any questions so far? Okay, so then I'll go on to the questions. Sorry, I'm having a little cohomologically rigidity. So if you haven't seen this before, so let F be a family of manifolds and pick 2 manifolds, M and M prime, in your family. So if M and M prime are diffeomorphic, then we all know that the cohomology of M is isomorphic to the cohomology of M prime, and that's as rings. And the question is, does the converse hold? So if we know that the rings are isomorphic, does that imply that the manifolds are diffeomorphic? And if the answer is yes, then we're going to say that the family is cohomologically rigid. Now, this is a very greedy thing to ask for, right? Like it's not a generally true thing, but it is sometimes true. And so one example is that surfaces are cohomologically rigid. So we know that if they're orientable, all you need to know is the genus, which you can just read off of H1. Another, which is also very well known, maybe not quite as well known, is that Hirzebruch surfaces are cohomologically rigid. So if you go back to Hirzebruch surfaces, it's easy to see that these cohomology rings are going to be isomorphic if and only if both, like M and M prime, are both even or both odd. That's sort of just a very easy, explicit thing to check. And in fact, it's well known that all the even Hirzebruch surfaces are diffeomorphic and all the odd Hirzebruch surfaces are diffeomorphic. Now, of course, they're not biholomorphic, and that's kind of the point of Hirzebruch surfaces, I think, historically, is the different holomorphic structures on the same underlying manifold. And so, however, so even though I said things are almost never cohomologically rigid, it's very special, there was a very sort of bold conjecture by Masuda and Su, which is, are all toric manifolds cohomologically rigid? And this is a very strong conjecture, but there has been some evidence that it's true. And the theorem I want to speak to you especially about is a theorem, a special case was proved by Masuda and Penoff, and then proved in general by Choi and Masuda, which states, let X and X prime be Bott manifolds. And I want to assume that both of them have rational cohomology, which is isomorphic to the rational cohomology of P1 to the n. So in this case, if their integer cohomology rings are isomorphic, then the manifolds themselves are diffeomorphic. So in the language I used before, if we look at the family of Bott manifolds with trivial rational cohomology, that family satisfies cohomological rigidity. And cohomological rigidity also holds in a number of other special cases. This is due to Cho, Choi, Lee, Masuda, Panoff, Park, and Su. But all of these are still pretty special cases. There's definitely generalizations of this, but it's usually other Bott manifolds or something called generalized Bott manifolds, which is similar to Bott manifolds, but you allow PJs instead of P1s. And the important thing is there's no known counterexamples. So this conjecture still very well might be true. So what I'm looking at is symplectic cohomological rigidity. So now we're going to let G be a family of symplectic manifolds. And we're going to fix two elements in this family. So now, if we know that M and M prime are symplectomorphic, then obviously, again, there's an isomorphism of rings from the cohomology ring of M to the cohomology ring of M prime. And this takes the cohomology class of omega to the cohomology class of omega prime. So, but again, we can ask, is the converse true? So suppose that you have an isomorphism from the cohomology of M to the cohomology of M prime, and that it takes the class of omega to the class of omega prime. Does that imply that M is symplectomorphic to M prime? Well, if the answer is yes, then G is symplectically cohomologically rigid. So an example, a very well-known example is that symplectic surfaces are symplectically cohomologically rigid. So if you want to classify surfaces up to symplectomorphism, you just need the genus and the area. And of course, the area is given by the cohomology class. So it still works. And also fairly well known is that symplectic Hirzebruch surfaces are also symplectically cohomologically rigid. If you go back, we said they were classified up to diffeomorphism just by whether it's even or odd, which gives you the ring. And then if you want them up to symplectomorphism, you need to know the total area of the polygon. And you need to know basically that this width here on the bottom is the same in the two cases. And it's very easy to check that that satisfies them up to ring isomorphisms, taking cohomology classes, and it's sort of been well known for a long time that that satisfies them up to symplectomorphism. I don't actually know who first proved it. It was well known like 30 years ago, but it follows from, for example, Yale-Karchan's paper. Okay. So this is the question I am looking at. The question is, are symplectic toric manifolds symplectically cohomologically rigid? So that's, say, we have a very ambitious, smooth conjecture. Let's go ahead and make the same symplectic conjecture. Now, there's much less that was known in this case. The most important theorem is due to McDuff. And if you have a symplectic toric manifold, and you know that the cohomology ring is isomorphic to that of pi cross pj, then you know it's symplectomorphic to pi cross pj. So, and of course, it will be the symplectic form where your cohomology class goes. So it is true in that special class. There's other partial results due to Karchan, Kessler, Knussalt, and McDuff, but those are mostly like finiteness results rather than on the nose. So this is the background and my question. Are there any questions? Okay, then we'll talk about our results. Oops. Okay, so our main theorem is the exact counterpart to the theorem I mentioned before. So let M and M prime be symplectic Bott manifolds. And again, I'm going to assume that the rational cohomology ring of M and the rational cohomology ring of M prime are both isomorphic to the rational cohomology ring of P1 to the N. In that case, if I have an isomorphism from the cohomology of M to the cohomology of M prime, and it takes the class of omega to the class of omega prime, then the manifolds are symplectomorphic. So in particular, if you're not that happy with Bott manifolds, this has a corollary, which is maybe a little friendlier. If there's a symplectic toric manifold and the cohomology ring of M is isomorphic to the cohomology ring of P1 to the N over the integers, then M is symplectomorphic to P1 to the N with one of the standard symplectic forms. So I just want to take the Fubini-Studi forms and pull them back and multiply them by some constant. So that's sort of the standard product form. And it's very easy to see that this follows from the theorem. And the reason is that Masuda and Penna prove that in this condition, M is a symplectic Bott manifold. So I can just apply the previous theorem. So for those of you who have happened to have seen cohomological rigidity, there's also a version called strong cohomological rigidity, which means that given an isomorphism, you have a symplectomorphism, which induces this isomorphism, and that also holds. But I don't want to focus on that. Okay. So for the rest of the talk, I'm going to talk about how do we prove this, and this is where toric degeneration comes in. So the proof of the main theorem, and the key step, the part that makes this sort of hard, is that we need to construct a new symplectomorphisms. And otherwise, the proof is quite similar to the smooth case, and I'm not really going to talk about it. But we need to prove this one proposition. So let M and M prime be symplectic Bott manifolds, and assume that we have some K less than L, and an isomorphism from the cohomology ring of M to the cohomology ring of M prime that takes omega to omega prime. So that's the standard thing. But now I need to have some very specific additional property, is I need this isomorphism to take xk to xk prime minus gamma xl prime for some gamma in Z, and xi to xi prime for all I not equal to k. So it's a special class of isomorphisms. I also need a technical condition, which is, remember I had this matrix A, and I want that if I take the LKth component of these two matrices and add them, I'm going to get something non-negative. And that's kind of easily fixed just by kind of flipping the varieties over. So what I'm going to focus on the rest of the time is just how do I prove this proposition? How do I construct my new symplectomorphism? Are there any questions? Okay, so I'll start talking about how to prove it. So the main tool is toric degenerations. And I'll go through this slide fairly quickly because we've talked about it before. But let X be inside Pn be any smooth projective variety. And I want to fix a local coordinate system on X. So I want to identify a neighborhood of some point with Cn, where little n here is the dimension of my manifold. And of course, you may have seen in other talks this afternoon, people talk about valuations. This is one way of getting valuations, but it's pretty general. So once you do this, you can define an associated semigroup. And again, we heard a little bit about how to define this in earlier talks, but all I want to think about is it's a semigroup inside Z cross Z to the n. And I want to think of it as the union of M greater than 0 of M cross S to the n. So Sm is just the layer of this semigroup on the level M. So once I've done this, I can define an Akunkov body. And what I take is I just take my semigroup Sm, I divide it by M, I take the union over all of those, I take the convex hull, and I take the closure. Great. And then I have a theorem by Harada and Kaveh, which is assume that this semigroup S is finitely generated. The first fact is that if I let X naught be proj of C of S, this is a projective toric variety with moment polytope delta. So of course it's not generally smooth and may not be normal, but anyway, it's a projective toric variety. And there's a continuous surjective map phi from X to X naught that's a symplectomorphism on an open dense subset of X. So in the previous talks, they usually talked about getting a set of functions on X, which were completely integrable. And in that case, they're just pulling back the moment map from X naught that gives you functions on X. So the key observation that we really need is that if X naught is smooth, then this map phi is a symplectomorphism. So this is a very special thing, though in general, X naught is not smooth. This process of finding a coordinate system and taking a semigroup is pretty violent. And so generally speaking, it induces singularities, but maybe it doesn't. And if it doesn't, then you actually get a symplectomorphism between them. And as Benjamin mentioned, the idea of this is we construct a toric degeneration of X. So it's a flat family. So the fibers over 0 is X naught, and the fibers over all other points are X. And then we're going to lift a radial vector field and construct a flow and then exponentiate it. That's the general idea. Okay, great. So this is toric degenerations, and how do we use them? Well, the way we use them is through something we call the slide operator. So first of all, we have to fix a vector. We have to fix an integral vector, and we don't want all the coordinates to be positive. At least one coordinate has to be negative. In this case, I can construct the slide of any subset of z to the of the positive quadrant in z to the n. And what I just do is I slide every point along W as far as possible within the positive quadrant in the direction W. So let's see what this does in this example. So you see here, we're sliding along the red arrows, and here we can't slide, here we can't slide, here we can't slide, but you see this point right here, there is room to slide it. I can slide it one position here, and now I get this picture. So I go from this picture to this picture by sliding along the red arrows. And the claim is, let M and M prime be symplectic toric manifolds with moment polytopes delta and delta prime. And I want them to be equal to the positive orthant near 0. So just like we have here, I want to just put them in that position. If there exists K less than L and C greater than or equal to 0, so that if I slide delta, well, the integral points in a multiple of delta, but I think about it sliding delta along the direction minus EK plus C to the L, then I get delta prime. So I can get from one polygon to the other by sliding the integral points. If I can do that, then M is symplectomorphic to M prime. So you look in this example and you're like, great, this was P1 cross P1, and this was the Hirzebruch surface sigma 2. And you can see I get from one to the other by sliding, and that tells me that these two symplectic manifolds are symplectomorphic. So, which is well known, but just a way of visualizing that symplectomorphism. So great. So how do we use this to prove our theorem? Well, remember that the hard thing we had to prove was proposition star, which said let M and M prime be symplectic Bott manifolds. And I wanted to assume that I had an isomorphism of a particular kind, and that this quantity C was greater than or equal to 0. I want to prove that those manifolds are symplectomorphic. And the proof is now very simple, that you check that if you're in the situation of this proposition and you slide the polytope delta in the direction minus EK plus C to the L, then you get the polytope delta prime. So this is a simple thing that you just need to check, like it's really just a check on the level of polytopes. It's a very hands-on convex geometry type of thing. And you check that this is true, okay, or backwards. So it's going to be a slide one way or the other. It's not sticking both ways. And then we're done, right? Because we know that in this situation, we can slide one polytope to the other, and that gives us, and then we apply this claim, and that tells us that they're symplectomorphic. And by the way you prove the claim is we construct very explicit coordinate charts, and you just apply Harada and Kaveh. So I think I'm out of time, but I'm done my talk.